Our nearest stellar neighbor just revealed something that should not be there, and then it vanished. In August of 2024, the James Webb Space Telescope turned its mirror toward Alpha Centauri, the closest star system to Earth, and found a faint object sitting in the dark near Alpha Centauri A. Something roughly the mass of Saturn, glowing quietly in mid-infrared, separated from the star by about twice the distance between Earth and the Sun. The team looked at the data carefully. They ran the analysis, a planet candidate around the nearest Sun-like star. The implications were staggering. Then they looked again in February of 2025, and it was gone. They looked in April. Still nothing. Researcher Aniket Sanghi put it plainly. "We are faced," he said, "with the case of a disappearing planet. Alpha Centauri is not some remote abstraction. At 4.37 light-years away, it is the target humans have pointed to for generations when imagining what interstellar travel might one day mean. The closest stars we will ever realistically study up close. And somewhere inside that system, according to one observation on one night in 2024, something was orbiting. Something real enough to register. Something that by February had moved beyond the edge of what the telescope could see, or had never been there at all. That uncertainty is what makes this worth understanding fully. Tonight, you will see what the telescope found, why it disappeared, and what the math says about whether it is still out there. Now look up. We begin. At 4.37 light-years away, Alpha Centauri is the closest star system to Earth, which in practical terms means it is roughly 25 trillion miles away. That number is worth sitting with for a moment. 25 trillion miles. The distance from New York to Los Angeles is about 2,800 miles. The distance to the Moon is roughly 239,000 miles. The distance to the Sun is 93 million miles. Alpha Centauri is 25 trillion. There is no ground-level analogy that makes this comfortable. The number simply refuses to fit inside anything a human being has ever experienced firsthand. What makes it stranger is that this is the close one. Alpha Centauri is not some remote object at the edge of the galaxy. It sits in our immediate cosmic neighborhood, the nearest stellar address to our own. Every other star system is farther. Some are hundreds of light-years away. Some are thousands. Alpha Centauri is 4.37 light-years, and even that is an almost incomprehensible distance. Light, traveling at 186,000 miles per second, takes 4 years and 4 months to make the crossing. A radio signal sent from Earth today would arrive sometime in 2029. The system is not one star, it is 3. Alpha Centauri A and Alpha Centauri B form a binary pair, 2 stars locked in a gravitational embrace, orbiting each other once every 80 years. From Earth, they appear as a single point of light, the third brightest star in the entire night sky. Separate them, and you have 2 distinct suns sitting roughly 11 to 36 astronomical units apart, depending on where they are in their orbit. A range that stretches from the inner edge of our solar system's gas giant territory out to well beyond Neptune. They are close companions by stellar standards, close enough that their combined glow has confused observers for centuries. The third member of the system is Proxima Centauri. It is a red dwarf, much smaller and dimmer than the other 2, sitting about 13,000 astronomical units away from the central pair on a slow, sweeping orbit that takes roughly 550,000 years to complete one loop. Proxima is currently the closest individual star to our Sun, marginally closer than A and B at about 4.24 light-years. But it is a faint ember compared to its companions, invisible to the naked eye despite being our single nearest neighbor. Its claim to fame is primarily one of geometry. Alpha Centauri A is the star that demands attention. In almost every measurable way, it resembles our Sun. Its mass is about 1.1 times the Sun's mass. Its diameter is roughly 1.2 times the Sun's diameter. Its surface temperature sits close to the Sun's surface temperature. Its absolute brightness is slightly higher, but not dramatically so. Its age is estimated at around 5 to 6 billion years, which puts it in the same broad life stage as our own star. If you took our Sun and made a slightly larger, slightly warmer copy, you would have Alpha Centauri A. This matters enormously, and we will come back to why. Alpha Centauri B is somewhat smaller and cooler, about 0.9 times the Sun's mass, visibly orange where A is yellow-white. It is still a solar-type star by most definitions, just a dimmer and more compact version. Together, A and B represent the nearest example we have of a Sun-like stellar environment outside our own backyard. Now consider the gulf that separates us from all of this. The fastest spacecraft humanity has ever launched is NASA's New Horizons probe, which left Earth in 2006 and flew past Pluto in 2015. It is currently traveling at roughly 36,000 miles per hour, making it one of the fastest objects humans have ever put into motion. At that speed, New Horizons has spent nearly 2 decades reaching the outer edge of our own solar system. It is not close to Alpha Centauri. It will not be close to Alpha Centauri in any meaningful time frame. At its current velocity, reaching the Alpha Centauri system would take somewhere in the range of 18,000 years. Not 18 years. Not 180 years. 18,000. That is the tension buried inside the phrase nearest star system. By the standards of interstellar space, Alpha Centauri is practically next door. By any standard a human being can actually feel, it is so far away that our fastest machine launched in living memory would still be traveling when civilizations that do not yet exist have risen and fallen. The universe operates on scales that are technically expressible in numbers and emotionally impossible to absorb. This is the system that JWST turned its instruments toward. This is the neighborhood, both the closest we will ever get to a Sun-like stellar pair and the most unreachable destination in any practical human sense. Alpha Centauri A and Alpha Centauri B have been studied for centuries. Their motions are mapped, their temperatures are catalogued, their spectra have been analyzed with extraordinary precision. Everything about them, down to the fine structure of their light, has been examined in painstaking detail. And for all of recorded history, nobody had ever confirmed a single planet orbiting either of those two Sun-like stars. The reason Alpha Centauri A has been on astronomers' radar for decades has nothing to do with it being exotic and everything to do with it being familiar. It is not a strange object. It is not a cosmic oddity. It is, by almost every physical measure that astronomers use to classify stars, a near-perfect copy of our own Sun. Similar mass, similar diameter, similar surface temperature, similar age. That familiarity is exactly the point. When you want to understand whether planets like ours can form around stars like ours, the most valuable place to look is the closest star that matches those conditions. Alpha Centauri A is that star? The numbers bear this out. Alpha Centauri A carries roughly 1.1 times the mass of our Sun. Its diameter is about 1.2 times wider. Its surface temperature sits within a few hundred degrees of the Sun's own 5,778 Kelvin. It is approximately 6 billion years old. That matters enormously. That is older than our own solar system. Old enough for whatever chemistry was going to happen around it to have had time to happen. If planets formed around Alpha Centauri A, they have had billions of years to develop, to cool, to accumulate water, to cycle through whatever geological processes rocky worlds go through. Age is not a trivial detail when you are thinking about the conditions that produce complex chemistry. The cultural weight behind this search is real, and it would be dishonest to pretend otherwise. Alpha Centauri has been the destination of choice in science fiction for generations. James Cameron chose it deliberately when he placed the moon Pandora in orbit around a gas giant circling Alpha Centauri A in the Avatar films. That choice was not arbitrary. It was the obvious answer to the question of where humans might someday go. The system appears in novels, films, serious scientific proposals for interstellar probes because it represents the first plausible stop beyond our own solar system. That cultural history does not change the physics, but it does reflect something genuine, the intuition, shared by scientists and storytellers alike, that if life is going to be found anywhere nearby, the nearest sun-like stars are the place to look first. There is, of course, already a known planet in the broader Alpha Centauri system. Proxima Centauri B was confirmed in 2016. It carries at least 1.3 times Earth's mass. Its orbital period of 11.2 days keeps it within Proxima's habitable zone. On paper, that sounds significant. In practice, the picture is considerably more complicated. Proxima Centauri is a red dwarf, a small, dim, violent star prone to powerful flares that blast high-energy radiation outward with little warning. The same proximity that puts Proxima B in the habitable zone also locks it in close enough that stellar flares could strip its atmosphere over geological timescales. Whether Proxima B retains an atmosphere at all, let alone a stable one, remains genuinely uncertain. Proxima Centauri C and D have also been identified. But the situation around Proxima is not the calm, Earth-like environment that would make any of these worlds easy to think about as targets for life. Alpha Centauri A and B are different in character. They are quieter stars, more stable, the kind of stars where, if a planet forms in the right place, the environment does not immediately work to destroy whatever might develop there. A planet orbiting Alpha Centauri A in a temperate zone would be receiving energy from a familiar kind of source, at a familiar rate, without the constant bombardment of energetic flares that complicates everything around Proxima. That difference matters when you are trying to assess whether a world might remain habitable over billions of years. The scientific prize is specific, and it is large. A confirmed planet around Alpha Centauri A would be the nearest known world outside our solar system orbiting a star that genuinely resembles our own. Not a red dwarf, not a hot young star, not an exotic object, a sun-like star, 4.37 light-years away. That proximity transforms what future study of such a world would look like. Most exoplanets we know about are hundreds or thousands of light-years distant, so far that even our best telescopes can extract only rough atmospheric signals. broad chemical fingerprints at best. A planet around Alpha Centauri A would be close enough to study in detail that no other known system could offer. Atmospheric composition, seasonal variation, cloud structure, the kind of planetary characterization that requires proximity. It would become the most studied world beyond our own solar system, essentially by default, simply because of where it sits. But wanting a planet to be there and actually finding one are two very different things. For a long time, the search kept coming up empty. The first serious attempt to find a planet around Alpha Centauri using modern methods came in the early 2000s, and it went nowhere. The method astronomers reached for first was radial velocity, one of the most proven tools in planet detection. The idea is straightforward. A planet orbiting a star does not simply circle a stationary object. Both the star and the planet pull on each other, and the star wobbles in response to that gravitational tug. The wobble is tiny, but it produces a measurable shift in the star's light. As the star moves toward us, its light compresses slightly to shorter wavelengths. As it moves away, the light stretches to longer ones. Sensitive spectrographs can read these shifts with remarkable precision, and from the pattern of shifts, astronomers can work backward to infer a planet's mass and orbital period. This technique had found hundreds of planets around other stars. It seemed like the obvious place to start with Alpha Centauri. The problem was the system itself. Alpha Centauri A and B orbit each other on an 80-year loop, which means they are constantly pulling on each other in addition to any planets that might be present. Separating the gravitational signal of a small planet from the enormous background noise of a binary companion is extraordinarily difficult. Researchers spent years accumulating radial velocity data on both stars, running the numbers through increasingly refined statistical filters, trying to isolate a planetary signal from the noise. Nothing credible emerged. The binary system was, in effect, drowning out the signal any planet would have produced. Then came 2012. A team announced that they had done it, found a planet orbiting Alpha Centauri B, close in, roughly Earth mass, completing a full orbit in just over 3 days. The excitement was immediate and enormous. Headlines ran worldwide. Alpha Centauri, already the most romanticized star system in popular imagination, had apparently confirmed a planet. For a few months, it seemed like the long search was over. Within 2 years, other researchers began picking apart the statistical analysis, and by 2015, the consensus had shifted decisively. The signal was not a planet. It was a ghost in the data, a mathematical artifact produced by the way the radial velocity measurements had been sampled and processed. The star had not wobbled because of a planet. The numbers had wobbled because of the method. The planet was erased from the record. That failure carried a particular sting. It was not simply a case of ambiguous data. It was a case of a signal that looked exactly like a planet, passed peer review, generated global attention, and then turned out to be an illusion produced by the noise floor of the instrument and the statistical treatment of the data. After that episode, any future radial velocity claim about Alpha Centauri would face an extremely high burden of proof. The field had been burned once. Nobody wanted to repeat it. Transit detection was never a realistic option. When a planet crosses in front of its star from our line of sight, it produces a measurable dip in the star's brightness. This method has found thousands of confirmed planets around other stars. But for it to work, the planet's orbit has to be nearly perfectly aligned with our viewing angle. The planet must actually pass between us and the star as seen from Earth. The probability of that alignment existing for any given planet is low, and for Alpha Centauri, it was not something astronomers could engineer around. Either the geometry worked or it did not, and there was no way to know without watching for years and hoping for a dip that might never come. Direct imaging was always the most appealing option in principle. Rather than inferring a planet from its gravitational effects or its shadow, you simply take a picture and see it. The appeal is obvious. The difficulty is staggering. Alpha Centauri A alone is the third brightest star in the entire night sky as seen from Earth. A planet orbiting it would be thousands of times fainter, emitting its own heat in infrared wavelengths, yes, but still overwhelmed by the star's output. Trying to image a planet next to Alpha Centauri A is something like trying to photograph a candle flame positioned next to a searchlight, with a second searchlight only a short distance away, adding its own wash of light across the entire field of view. That second light source is the crux of the problem. Alpha Centauri B is never far from A in the sky. Depending on where the two stars are in their 80-year orbit, B can appear anywhere from a few arcseconds to roughly 22 arcseconds from A. Either way, it is always in the frame. The two stars together create a layered glare pattern in any imaging instrument, a central blinding peak from whichever star you are targeting, surrounded by complex diffraction rings and spikes, and then the additional glow of the companion sitting somewhere in the same field. Any faint object a planet's brightness would require detecting in that mess gets lost. The interference is not a minor annoyance. It erases exactly the signal you are looking for. Ground-based telescopes were fighting this problem on top of another one, Earth's atmosphere. Even at the best observatory sites in the world, atmospheric turbulence blurs the fine structure of starlight in ways that obscure faint companions. Adaptive optics systems helped, but not enough. Year after year, the system most people assumed would be the first place we found a nearby planet resisted every tool the field had developed. What the field needed was not a better technique for the old methods. It needed an entirely different kind of telescope. The James Webb Space Telescope was not built to look at Alpha Centauri. That is not a criticism. It is just the truth about what the telescope was designed to do. Understanding the gap between that design and what actually happened in August 2024 is essential to understanding why the detection matters at all. JWST was conceived as a machine for looking backward in time. The universe has been expanding since the Big Bang. That expansion stretches light. Wavelengths that started out as visible or ultraviolet radiation get pulled out over billions of years of travel into the infrared portion of the spectrum. The most ancient galaxies, the first structures that formed after the universe, cooled enough to allow stars to ignite, emit light that arrives here so stretched and so faint that no visible light telescope could detect it. JWST was built specifically to catch that light. Its primary mirror spans 6.5 meters across, 18 gold-coated hexagonal segments that unfold in space like a mechanical flower, and it operates almost entirely in infrared wavelengths where that ancient red-shifted signal lives. To protect those infrared instruments from interference, the telescope has to be extraordinarily cold. infrared detectors are sensitive to heat, including the heat of the telescope itself. Any warmth bleeds into the data as noise. So JWST sits at the second Lagrange point, a gravitational parking spot roughly 1 million miles from Earth in the direction directly away from the Sun. There, a 5-layer sunshield the size of a tennis court keeps the instruments permanently shaded, cooling the telescope's cold side down to around negative 233 degrees Celsius, close to absolute zero. This is not a minor engineering footnote. The cold is the whole point. Without it, the thermal noise from the telescope structure would drown out the faint infrared signals JWST was designed to detect. None of that was conceived with Alpha Centauri in mind. The science cases that drove JWST's design were cosmological: the formation of the first galaxies, the atmospheres of transiting exoplanets, the dust clouds where stars are being born right now in regions of our own galaxy that visible light cannot penetrate. Alpha Centauri sits just 4.37 light-years away. On the scale of distances JWST normally thinks about, that is essentially in the parking lot. But here is where the physics turns interesting. The same sensitivity that allows JWST to detect a galaxy 12 billion light-years away also makes it extraordinarily capable of detecting faint infrared sources nearby. More importantly, the telescope's mid-infrared instrument, called MIRI, the mid-infrared instrument, operates at wavelengths between roughly 5 and 28 microns. This is a critical band. At those wavelengths, warm objects do not just reflect light, they emit their own. A planet does not need sunlight to glow in the mid-infrared. It needs only to have some internal heat, some residual warmth left over from its formation. It will radiate in this band on its own. Gas giants retain heat for a very long time. A Saturn-mass world, even billions of years old, will still be warm enough to emit detectable thermal radiation in the mid-infrared. Visible light telescopes looking at the space around a star are trying to catch reflected starlight bouncing off a planet. This is a brutal problem. The star is billions of times brighter than the planet's reflected signal. In the mid-infrared, the star is still much brighter than the planet, but the ratio is more survivable. The planet is contributing its own energy to the signal rather than just borrowing light from its host and returning a tiny fraction. MIRI's wavelength range is not just a design feature for the specific challenge of finding old, cool gas giants around nearby stars. It is an advantage that no previous space telescope had. This still did not put Alpha Centauri on JWST's original schedule. The telescope's observation time is allocated through a competitive proposal process. Scientists submit requests, panels evaluate them, and time is awarded based on scientific merit. The team that eventually observed Alpha Centauri A in 2024 had to make a case that the system was worth the telescope time, a harder argument to make than it sounds. This was because the two stars orbit each other closely enough that their combined glare creates serious technical complications. Alpha Centauri B is always somewhere nearby in the image, adding its own infrared glow to whatever the telescope is trying to examine around Alpha Centauri A. The observation sequence the team needed to use did not exist yet. The Space Telescope Science Institute's operations staff had to develop it specifically for this target. Nobody had run this particular play before. Problems like this are only overcome when someone decides it is worth solving and keeps pushing until the infrastructure catches up. The scientific justification was real. The nearest Sun-like star, the closest possible target. A detection technique that had never been tried at this distance, but the logistics required original work. A custom observing sequence. A careful calibration approach. A strategy for subtracting the residual light from both stars after the primary glare was blocked. The team had to build a methodology from scratch before they could point the telescope, and once they had it, they needed one more thing. Because even with JWST's sensitivity in the mid-infrared, the light from Alpha Centauri A is still overwhelming, thousands of times brighter than anything a planet around it could produce. Without some way to eliminate that glare at the source, every image would be a wash of stellar light with nothing visible inside it. The piece of technology that made the difference was something called a coronagraphic mask. It is the reason any of this was possible at all. Alpha Centauri A is not simply a bright star from our vantage point in the southern sky. It is the third brightest object in the night sky after the Sun and Sirius. It outshines everything visible from Earth except one star and the Sun itself. That is extraordinary company to keep. And it creates a problem that is almost comically severe when you are trying to find a planet orbiting around it. Here is the core difficulty. Any planet circling Alpha Centauri A reflects only a tiny fraction of the star's light, emits a modest amount of its own thermal radiation. The brightness ratio between the star and a Saturn-sized world sitting 2 Earth-Sun distances away is somewhere above 10,000 to 1. In mid-infrared wavelengths, where JWST's MIRI instrument operates. The contrast is somewhat more favorable than in visible light because warm planets glow with their own heat rather than just bouncing starlight back at you. But the gap is still enormous. Looking for this planet without somehow suppressing the star's light is like standing a mile from a stadium during a night game, trying to spot a single firefly hovering near one of the floodlights. The floodlight doesn't just make the firefly hard to see, it effectively erases it from existence. The solution astronomers developed for exactly this kind of problem is called a coronagraph. The name comes from solar astronomy. For decades, solar telescopes have used physical disks to block out the face of the sun so that the faint corona around it, the outer atmosphere, becomes visible against dark sky rather than being drowned in solar glare. The same principle applies at much greater distances. A coronagraphic mask is placed inside the telescope's optical path, positioned to block the light from a target star before it ever reaches the detector. With the star's direct light removed, objects thousands of times dimmer sitting nearby can register. JWST's MIRI instrument carries coronagraphic masks designed for exactly this purpose. The masks come in different shapes and sizes, optimized for different targets and separations. For Alpha Centauri A, the team used a specific mask calibrated to suppress the star's light across the region, where a planet at roughly 1 to 2 astronomical units would appear in the image. In principle, that should reveal the planet. In practice, it revealed a much harder problem. Blocking a star with a physical mask does not make the star disappear entirely. The mask stops direct light, but the optics of the telescope itself scatter some of that light into diffraction patterns, rings, spikes, arcs of residual glow spreading outward from where the star sits behind the mask. These patterns are predictable in theory and can be modeled, but they are not perfectly predictable. any slight imperfection in how the mask aligns with the star leaves behind structured noise. For nearby targets like Alpha Centauri, where the star is so overwhelmingly bright that even tiny fractions of its light slipping past the mask are significant, this residual scattered light is a serious obstacle. You are not working with a clean dark field. You are working with a complicated, subtly glowing mess. And then there is Alpha Centauri B. The two stars orbit each other at separations ranging from about 11 to 36 times the Earth-Sun distance. That means B is always somewhere nearby in the image. It cannot be masked simultaneously with A using the same coronagraphic element. So while the team is trying to see something faint near A, the neighboring star is sitting in the field of view, adding its own structured glare, its own diffraction patterns, its own noise floor to the image. The two sets of interference patterns overlap and combine in ways that require careful modeling to disentangle. The team's solution was to build a subtraction process. They constructed a detailed model of what the combined residual light from both Alpha Centauri A and Alpha Centauri B should look like under the coronagraph, accounting for the optical characteristics of MIRI, the positioning of both stars, the specific observing geometry. Then they subtracted that model from the raw image. What remained after the subtraction, the residual after removing everything you could account for, was the signal they were hunting. This is not a novel technique in astronomy. Sophisticated point spread function subtraction is standard practice in high contrast imaging. But applying it to Alpha Centauri at JWST's sensitivity level required a custom observing sequence that the operations team developed specifically for this target. The standard pipeline was not going to be enough. What the process ultimately achieved was the ability to detect sources more than 10,000 times fainter than Alpha Centauri A itself. Within the angular region around the star, where a planet on a stable orbit might actually survive the gravitational influence of Alpha Centauri B. No telescope before JWST had been able to reach that contrast threshold at that angular separation for a star this close. Previous instruments either lacked the sensitivity, lacked the right coronagraphic elements, or were overwhelmed by the extreme brightness of the target before they could get anywhere near that depth. JWST, operating in mid-infrared where it was built to be uniquely powerful, made the arithmetic work for the first time. In August of 2024, after all of that preparation, the team finally pointed JWST's coronagraphic mask at Alpha Centauri A and looked. On an observation run in August of 2024, the team pointed JWST's MIRI instrument at Alpha Centauri A with the coronagraphic mask in position, blocked out the star's blinding glare, and found something that had not been there in any previous image. To understand the weight of that moment, you have to understand what the team expected going in. The goal was not necessarily to find a planet. The observing program had been designed in part to characterize the infrared environment around Alpha Centauri A, to map out the dust, to understand the thermal background, to establish a baseline. If something planetary was lurking there, that would be extraordinary. But the honest expectation was probably closer to a clean null result, or perhaps a faint smear of warm dust scattered through the inner system. What astronomers call a debris disk. Unremarkable, scientifically useful, and absolutely not a planet. What came back instead was a point source, a discrete blob of light sitting clearly separated from Alpha Centauri A, at a distance of roughly 2 astronomical units from the star, twice the distance between Earth and the Sun. It was sitting there in the MIRI data, unambiguous enough that it could not be dismissed as noise. The team subtracted the residual glare from both Alpha Centauri A and the nearby Alpha Centauri B, and the object remained. It was real in the data. The question was what it actually was. The brightness of this object told a story of its own. In mid-infrared wavelengths, where MIRI operates, a planet does not shine by bouncing starlight back toward the telescope the way a mirror would. Instead, a warm body radiates its own heat. Everything with a temperature above absolute zero emits thermal radiation, and in the mid-infrared, a planet warm enough to have retained internal heat from its formation will glow on its own terms, independently of how much light it receives from its star. The detected object was doing exactly that. Its mid-infrared brightness was consistent with a body emitting thermal radiation at temperatures comparable to the giant planets in our own solar system, cool by stellar standards, warm enough to register clearly in MIRI's wavelength range. The object was more than 10,000 times fainter than Alpha Centauri A itself. That number sounds disqualifying until you remember that the entire point of the coronagraphic mask and the image subtraction pipeline was to make detections at exactly this contrast ratio possible. The system had worked as designed. Better, arguably, than many had dared to hope. The team's first serious question was mass. How big would an object have to be, at that distance from Alpha Centauri A, radiating that much infrared energy, to produce this signal? The answer the models kept returning to was a gas giant, not a rocky world, not a super-Earth. Something in the general mass range of Saturn, roughly 95 times the mass of Earth, give or take the substantial uncertainties that come with a single observation. A Saturn analog. In the nearest star system. 2 astronomical units from a star almost identical to our Sun. The reaction inside the team was, by all reasonable inference, not a celebration. It was the specific, controlled excitement of people who have been in this business long enough to know what ghost signals look like. Alpha Centauri has produced false positives before. In 2012, a separate research group announced a planet around Alpha Centauri B with significant fanfare, and that detection fell apart under scrutiny, a statistical artifact that had masqueraded as a signal for years before being formally retracted. That history was not abstract. It was a specific cautionary example sitting in everyone's memory. The 2012 detection had seemed convincing too, so the team did what careful scientists do. They wrote up the observation, they submitted it for peer review, they documented the image subtraction methodology and the brightness measurements and the mass estimates with the full weight of their uncertainty ranges attached. And before any of it became public, before they stood in front of anyone and said the word planet in connection with Alpha Centauri A, they scheduled follow-up observations. This is worth pausing on. The team had, in their data, what appeared to be a gas giant orbiting the nearest Sun-like star in the known universe. That is one of the most significant potential discoveries in the history of exoplanet science. It would end a search that had been running in various forms for decades. It would place a planet in a system that science fiction had been populating with imaginary worlds for more than half a century. James Cameron had already put a habitable moon around a gas giant in the Alpha Centauri system 20 years before this observation was taken. The cultural resonance alone was enormous, and the team held it. They prepared their paper. They pursued their follow-up observations. They did not announce. There is something worth recognizing in that restraint, because the pressure to announce, the pull toward being the group that found the first planet around Alpha Centauri, had to have been real. The fact that they did not move until they had tried to confirm the detection is the reason the subsequent story, complicated as it became, retained its scientific credibility. What they were waiting for was simple enough in concept. Point the telescope back at the same region of sky, find the same object sitting in roughly the same location, and the case for a real planet becomes dramatically stronger. The orbital motion of a planet on a roughly 2-year orbit is predictable. A real world would have moved somewhat, but it would still be there, still bright, still emitting in mid-infrared exactly as the models predicted. Before claiming they had found a planet around the nearest sun-like star, they needed to see it again. To understand why detecting this object was remarkable, it helps to know what direct imaging of exoplanets normally requires. Most of the exoplanet discoveries you have heard about over the last 30 years were not photographs. They were signals, indirect clues buried in starlight. The transit method watches a star's brightness drop by a fraction of a percent when a planet crosses in front of it. The radial velocity method measures the microscopic wobble of a star being pulled by a planet's gravity, a shift in light wavelength smaller than a single pixel on most detectors. These techniques are extraordinarily sensitive. They have found thousands of worlds, but they do not produce an image. They produce a pattern in data, and from that pattern you infer that something is there. Direct imaging is different. Direct imaging means you are actually detecting light from the planet itself, not a shadow, not a wobble. A signal from the object, arriving at your detector, separate from the star. This sounds more intuitive than indirect methods, but in practice, it is far harder. To image a planet directly, you need the planet to be bright enough to see against the overwhelming glare of its host star. And stars are not dimly lit objects sitting peacefully in the dark. They are nuclear furnaces pouring out light in every direction, tens of thousands to billions of times more luminous than any planet near them. The ratio in this case was more than 10,000 to 1. Alpha Centauri A against the detected object. Think of it this way. Imagine you are standing on the far side of a harbour at night. A lighthouse beam is sweeping across the water. Somewhere next to that lighthouse, someone is holding a single dim candle. Not a torch, a candle. Your job is to see the candle flame without looking away from the lighthouse. That is roughly the detection problem JWST was asked to solve in this observation, and it had to solve it while a second, nearly equally blinding light source sat just off to the side. The planets that have been directly imaged before this observation shared a few things in common. They were large, often several times the mass of Jupiter. They were young, still radiating the heat of their formation like a cooling ember, which made them intensely bright in infrared. And they were far from their stars, separated by enough angular distance that the telescope could resolve them cleanly. Distance from the host star is critical because the glare from a star does not stop at its surface. It spreads across any image as diffraction patterns, rings and spikes produced by the telescope's own optics. Objects close to the star drown in this residual light. The rule of thumb in direct imaging, for most of its history, has been to look for planets that are far out and hot and young, because those are the ones you might actually see. What JWST found near Alpha Centauri? A breaks that framework in every direction. The object is close to its star, sitting at roughly twice the Earth-Sun distance. That is well inside the region where diffraction glare from Alpha Centauri A is still significant. It is not young and glowing with formation heat. The temperature estimates from the infrared brightness put it in the range of a mature, cool gas giant, more comparable to Saturn or Jupiter than to the hot young giants that previous direct imaging campaigns found. It is not exceptionally massive. The brightness in mid-infrared suggests something roughly Saturn-sized, not a super Jupiter. By every conventional standard for what direct imaging can find, this object should not have been detectable. The fact that it was detectable came down to three things. JWST's mirror is large enough to collect the faint infrared signal. MIRI observes at mid-infrared wavelengths where warm planets glow with their own thermal emission rather than relying on reflected starlight, which gave the team a signal that was as strong as it could possibly be for an object at this temperature. And the coronagraphic mask, combined with the careful mathematical subtraction of residual starlight, suppressed Alpha Centauri A's glare enough to reveal something more than 10,000 times fainter, sitting in what had previously been a blind zone. The team pushed the instrument to a sensitivity that had not been demonstrated for a target this close to such a bright star. The observation was not routine. It was, by the team's own account, operating near the edge of what the telescope was designed to do. The result was a faint blob of infrared light, clearly separated from the masked-out star, in a position consistent with an object orbiting at a planet-like distance. That was August 2024. Then the February follow-up observations happened, and the object was gone. In February of 2025, the team returned to Alpha Centauri A with JWST, expecting to see what they had found the previous August, and they found nothing. Not a faint signal. Not a degraded version of the August blob. Nothing. The coronagraphic mask went up, the residual starlight was subtracted, and where the object had been sitting clearly in the data 6 months earlier, there was empty space. The team processed the images again. They checked the observing conditions, reviewed the instrument settings, ran the subtraction pipeline a second time. The answer did not change. Whatever had been there in August 2024 was not there in February 2025. This is the moment where the emotional temperature of a research project can plummet very fast. The August detection had already been prepared into a paper and submitted for peer review. Colleagues had been briefed. The result was being quietly circulated among a small group of researchers who understood what it might mean. And now the follow-up observation, the one that was supposed to be the easy confirmation, the formality before the announcement, had come back empty. Anyone working on Alpha Centauri planets in 2025 had the same reference point sitting in the back of their mind. In 2012, a team announced a planet around Alpha Centauri B. It was a radial velocity detection, a tiny wobble in the star's motion that the team interpreted as a world roughly the mass of Earth on a very short orbit. The announcement generated enormous coverage. The nearest star system, a planet, potentially rocky, practically next door. Within 2 years, independent researchers showed the signal was a ghost in the data, a statistical artifact produced by the way the measurements had been processed. The planet did not exist. The 2012 result was retracted, and the field collectively absorbed an embarrassing lesson about how badly you can want something to be real. That history does not go away. It sits in the room at every Alpha Centauri result meeting, and in February of 2025, it was sitting very loudly. The team requested additional telescope time. In April of 2025, they got it. The access came through Director's Discretionary Time, a category of telescope allocation reserved for urgent situations, unexpected findings, or circumstances where waiting for the normal scheduling cycle would mean losing a scientifically critical window. Getting Director's Discretionary Time is not routine. It requires making a case that the science cannot wait. The team made that case, and the time was granted. April came back the same as February. No detection. The object that had appeared clearly in August 2024 was absent for the second consecutive observation. Aniket Sankhi, one of the lead researchers on the project, put it directly. "We are faced with the case of a disappearing planet." That line captures exactly what the situation felt like from inside the team. Not a planet that turned out to be wrong. Not a clean negative result that closes the book. A planet that showed up once, clearly and brightly enough to generate a paper, and then refused to show up again. 3 options were now sitting on the table, and none of them were comfortable. The first was the hardest to accept, but the most scientifically important to consider. The August 2024 detection was a false positive. Some artifact of the coronagraphic subtraction, some residual interference pattern from Alpha Centauri B's glare, some background source that happened to occupy that position in the image and was not actually associated with the Alpha Centauri system at all. Background galaxies and other faint sources exist behind every star field. MIRI's coronagraphic subtraction process, though extraordinarily precise, leaves residuals. It was at least conceivable that something in the image processing had created a convincing but artificial signal. The second option was the one the team believed was more likely, though belief alone doesn't get you published. The object was real. It was genuinely present in the Alpha Centauri system in August 2024, physically there, emitting thermal radiation that MIRI had detected at the correct sensitivity threshold. Between August and February, it had moved. Planet's orbit. A planet on a relatively tight elliptical path around Alpha Centauri A, completing a full loop every 1.5 to 2.5 years, would be in very different positions at different points in its orbit. If that orbit carried the planet back toward the star between August and February, the coronagraphic mask's inner working angle, the region too close to the star to see through the residual glare, might have swallowed it entirely. It wouldn't be gone. It would just be hidden again, tucked back behind the blinding curtain of starlight the coronagraph was designed to suppress. There was a third option that nobody was particularly eager to write in a paper, but that could not be formally excluded. Something stranger. An object that is not on a stable planetary orbit. A transient event, a cloud of material, a dust clump, something that exists and moves on timescales too unpredictable to fit into standard orbital models. The universe is not obligated to produce clean explanations, and Alpha Centauri has already demonstrated a talent for producing detections that do not behave the way they are supposed to. The paper was already in peer review. The team now had to revise what they were claiming. Not a confirmed planet, a candidate, a detection that is real but unconfirmed, with follow-up observations that are consistent with either a false positive or an object that has moved out of detectable range. Those are very different sentences than the ones the original draft had been written to contain. The honest version of the result was also the harder version to communicate. 1 detection and 2 non-detections. The object appeared once and vanished twice. What that actually means, whether it supports or undermines the August finding, is not a question you can answer by looking at the images again. What was needed now was math, a lot of it. The team ran computer simulations of millions of possible orbital paths to figure out whether a real planet could have been present in August 2024 and absent from JWST's detection range in February and April 2025. This is the kind of problem astronomers solve with math when the observations stop cooperating. You cannot go back and rerun August 2024. You cannot force the object to reappear. What you can do is build every possible orbit consistent with what you did see, run each one forward through time, and ask which ones also explain what you did not see. The starting point was the August 2024 detection itself. The object appeared at a specific angular distance from Alpha Centauri A, at a specific brightness, in a specific direction. Those 3 constraints immediately rule out most conceivable orbits. A planet moving on a circular orbit at that exact distance would have a predictable position at any future moment. The question was whether any of those positions placed it behind the star's residual glare in both February and April 2025. That calculation alone is not trivial, but it is manageable. What made the problem genuinely hard was Alpha Centauri B. This is not a single-star system. Alpha Centauri B orbits Alpha Centauri A on an 80-year cycle, swinging as close as 11 astronomical units and as far as 36. In our solar system, that range would cover the orbital territory from Saturn to well past Uranus. A companion star moving through that range does not just sit there passively. Its gravity reaches across the system constantly, tugging at anything orbiting Alpha Centauri A. Not every orbit that would be stable around an isolated star is stable here. Some orbits that look clean and predictable over a few years would be shredded over millions of years by the slow gravitational pressure of the companion. The team could not just simulate where a planet might be. They had to simulate which orbits were physically survivable over the long-term life of the system, and then work only within that constrained set. Running millions of paths through that filter takes serious computing. Each simulated orbit had to satisfy several conditions simultaneously, consistent with the August 2024 position, dynamically stable in the presence of Alpha Centauri B, and not producing a detectable signal in either of the 2 failed follow-up windows. The third condition is where the story gets interesting. When the team tallied the results, 52% of the stable orbital configurations that match the August 2024 detection were also fully consistent with a non-detection in February and April 2025. More than half. Not a fringe scenario, not a barely possible edge case. The most natural explanation for the disappearance under this analysis is simply that the planet moved. The geometry of this is worth holding in your mind. JWST's coronagraphic mask blocks the star, but the blocking is not perfect. There is always a zone immediately surrounding the masked star where residual diffraction and scattered light make faint objects undetectable, a bright halo of optical noise that swamps anything too close. If the planet follows an elongated elliptical orbit rather than a circular one, it would spend part of its year relatively far from the star and part of it swinging closer in. During August 2024, it was apparently at a favorable part of its orbit, far enough out to be sitting in detectable territory. By February 2025, the modeling suggests it had moved inward, not onto the star, but into that bright inner zone where the glare renders it invisible. The planet did not vanish. The planet moved somewhere. JWST cool. Do no longer reach it. The 2019 VLT data adds another layer. That earlier observation, taken 5 years before the JWST detection, may have caught a signal from the same object. The team incorporated it into the orbital modeling as an additional constraint. Not every orbital solution fits both the 2019 position and the 2024 position, but some do. The ones that fit both are the ones the team finds most credible, and they describe an object with an orbital period somewhere between 1.5 and 2.5 Earth years on a distinctly elliptical path. An elliptical orbit is exactly the kind that would produce a clear detection in one window and nothing in 2 others just a few months later. The math and the observations agree on that point. None of this constitutes proof. What it constitutes is a coherent physical picture that accounts for everything the team observed and everything they failed to observe. The alternative, that the August 2024 detection was a false signal, some imaging artifact or background source that happened to land at exactly the right position, does not disappear from the table. But a false signal would not be expected to align with the 2019 data. A false signal does not have an orbital period. The fact that a single physical object on a single orbit can explain 4 separate observations, including 2 failures, is the thing that keeps this candidate alive. The data does not contradict the planet. It actually expects it. What emerged from those millions of simulated paths was a picture of the kind of planet this might actually be. If the object is real, the data suggests it is a gas giant, not a rocky world, not a super-Earth, but something closer in character to Saturn. That distinction matters. When most people hear the phrase planet around another star, they picture something with a surface, land, maybe water, maybe atmosphere pressing down on solid ground. What the orbital modeling and the MIRI brightness data are pointing toward is a world made mostly of gas and cloud, with no crust underneath, no place to stand. A sibling to the outer planets of our own solar system, rather than to Earth or Mars. The mass estimate comes from the infrared brightness. In mid-infrared wavelengths, planets glow with their own stored heat, rather than simply reflecting starlight. How bright an object appears in those wavelengths, combined with its estimated distance from the star, lets astronomers work backward toward a mass. The answer the team keeps arriving at is roughly Saturn-mass, not Jupiter, not a super-Jupiter, not one of the bloated hot giants that weigh several times more than anything in our solar system. Something closer to the smaller of our 2 gas giants. Saturn contains about 95 times the mass of Earth. If that is what is sitting in the Alpha Centauri A system, it is a substantial world, but not an extreme one. It falls squarely within the range of planets our own sun produced. The orbit is elliptical. This is not unusual. Most planetary orbits are ellipses rather than perfect circles, including Earth's own, though Earth's is nearly circular by comparison. What the modeling describes for this candidate is an orbit stretched enough to carry it between roughly 1 and 2 times the Earth-Sun distance over the course of a single trip around Alpha Centauri A. At its closest point, it sits at approximately the same distance from its star as Earth sits from the Sun. At its farthest, it has moved twice that distance out. The full orbital period falls somewhere between 1.5 and 2.5 Earth years. In practical terms, this is a fast orbit, faster than Jupiter's 12-year loop, faster even than Mars's roughly 2-year circuit around our Sun. Now consider the temperature. Most of the gas giants that have been directly imaged around other stars are young and hot. Directly imaging a planet requires the planet to be bright enough to detect against the star's overwhelming glare. The easiest way for a planet to be bright in infrared is to be pumping out enormous amounts of heat. The planets we have successfully photographed around distant stars are often hundreds of millions of years old at most, still radiating the heat of their formation, glowing at temperatures that can reach several hundred degrees Celsius or higher. They are not like anything in our solar system. They are relics from early planetary youth, caught before they had time to cool. The Alpha Centauri candidate does not fit that profile. Alpha Centauri A is roughly the same age as our Sun, around 5 billion years old. A planet that formed around it when the system was young would have had 5 billion years to radiate away its formation heat. What you would expect, what the data appears to show, is a planet that has cooled to something far closer to the temperatures of Saturn and Jupiter than to those young blazing giants around distant stars. The infrared brightness puts the estimated temperature in a range that is genuinely comparable to the outer planets of our own solar system. This would make it one of the coldest exoplanets ever directly imaged, possibly the coldest. That is a significant threshold. Every gas giant directly photographed before this candidate was chosen, partly because it was anomalously bright and hot and therefore detectable. The technique of direct imaging has historically been limited to the easiest targets, the objects loudest in infrared. A cool old gas giant around a nearby star is a fundamentally harder object to detect. The fact that this candidate appears to be exactly that kind of object is part of why the team pushed JWST's instruments as hard as they did to pull the signal out. Put the pieces together and you get a picture that does not look like science fiction so much as it looks like a mirror. A gas giant, Saturn in mass, billions of years old, following an elliptical path around a sun-like star at distances that span the range Earth occupies in our own system. If this object is confirmed, it would not just be the nearest directly imaged exoplanet to Earth. It would be the exoplanet that most closely resembles the actual giant planets of our solar system in every measurable way. Mass, temperature, age, orbital character. Every one of those variables pointing towards something familiar rather than exotic. Researchers have used the phrase touchstone object to describe what it could become for exoplanet science. That phrasing is careful and deliberate. A touch tone is a reference point, something you measure other things against. There is one other detail about the orbit that tends to stop people mid-sentence when they hear it. The orbit of the planet candidate, as the modeling works it out, would keep it inside Alpha Centauri A's habitable zone for a significant portion of every lap around the star. That single fact tends to stop people. It stopped researchers too, though they were careful about how they described it. To understand why it matters, you need to know what the habitable zone actually means and, more importantly, what it does not mean. The habitable zone is not a region of guaranteed life. It is a region of possible liquid water. The definition is narrow and mechanical. At these distances from this particular star, a rocky world with a reasonable atmosphere could theoretically maintain liquid water on its surface. No more, no less. The zone is defined entirely by energy, how much radiation the star pumps out, and how far a planet must sit to receive neither too much nor too little. Our Sun's habitable zone runs roughly from the inner edge near Venus's orbit to the outer edge somewhere past Mars. Earth sits comfortably in the middle. Alpha Centauri A is slightly more massive than our Sun, slightly hotter, and slightly more luminous. Its habitable zone is shifted outward accordingly. The inner boundary falls at roughly 1.2 times the Earth-Sun distance. The outer boundary sits near 1.9 times that distance. The planet candidate's orbit ranges between 1 and 2 Earth-Sun distances from the star. For a significant stretch of every 1.5 to 2.5-year orbit, this object is inside that window. Here is the catch. It is a gas giant. There is no surface to stand on, no crust beneath an ocean, no bedrock, no shoreline, no atmosphere you could breathe. The planet is almost certainly a swirling envelope of hydrogen and helium, growing denser and hotter as you descend, with no clean boundary between atmosphere and interior. Life as we understand it requires a surface, a substrate, something to hold chemistry in place long enough for complexity to develop. A gas giant cannot provide that. So in the most literal reading of the question, this world is not habitable and probably never will be. But that is not actually where the interesting question lives. The interesting question is what orbits the planet. Every gas giant in our solar system carries moons. Jupiter has dozens. Saturn has dozens more, including Titan, which has lakes of liquid methane and an atmosphere thicker than Earth's. More relevant to this conversation, Jupiter's moon Europa is covered by a global ocean of liquid water beneath a shell of ice, kept from freezing entirely by the tidal heating of Jupiter's gravity. Saturn's moon, Enceladus, vents plumes of water vapor from a subsurface ocean through cracks in its southern ice cap. Europa and Enceladus are two of the most seriously discussed candidates for extraterrestrial life in the entire solar system, and neither one is a planet. Both are moons of gas giants. Both exist in conditions that are, at first glance, far harsher than Earth's. And yet, the chemistry is there. Now put a Saturn-mass gas giant in the habitable zone of Alpha Centauri A, 4.37 light-years away. If that planet has moons of any appreciable size, those moons are orbiting inside the habitable zone. They would receive the same energy budget from Alpha Centauri A that the planet itself receives. The tidal forces from a Saturn-mass host could generate internal heating in a moon the way Jupiter heats Europa. Water ice on such a moon might remain liquid beneath its surface. The conditions that exist in our own solar system's most biologically promising locations would, in principle, be reproducible there. Nobody is claiming this is the case. There is no observation of moons. There is barely a confirmed observation of the planet itself. But the orbital mechanics do not rule out moons, and they cannot rule out the chemistry that follows from moons in the right location. This is speculative. The researchers know it. But it is the kind of speculation that the data invites. What makes the habitable zone detail sit differently than a typical statistic is the address. Most exoplanets found in habitable zones orbit stars hundreds or thousands of light-years away. They are data points. They are brightness curves and spectral lines and probability calculations. This candidate, if it is real, is orbiting Alpha Centauri A, the closest Sun-like star to Earth, the one that lights up the southern sky on a clear night and has been visible to humans for as long as humans have looked up. The potential for liquid water in that system, on something orbiting that star, is not an abstraction. A gas giant in the habitable zone is not the same thing as a habitable planet, but it is not nothing either. Before JWST made its August 2024 observation, there was already a hint sitting in archived data from the ground. In 2019, the European Southern Observatory's Very Large Telescope in Chile, one of the most capable ground-based observatories ever built, was pointed at Alpha Centauri A as part of a broader effort to probe the system for faint companions. The instrument used was NIR, a specially modified mid-infrared detector designed in collaboration with the Breakthrough Initiatives program, whose explicit goal was hunting for planets around Alpha Centauri. The observation was a serious attempt by serious people with serious equipment. What came back from that run was ambiguous. There was a faint signal. It was not clean enough, not certain enough, to announce as a detection. The team published their results with appropriate caution, flagging a possible candidate, but stopping well short of claiming a planet. The astronomical community noted it and largely moved on. That is how it sat for 5 years. No follow-up observation could resolve it. Ground-based telescopes, even the Very Large Telescope, are fighting Earth's atmosphere on every exposure, and mid-infrared observations from the ground are brutally difficult. The signal was real enough to record and uncertain enough to set aside. Files go into archives. Other targets get scheduled. The hint from 2019 became a footnote rather than a headline. Then the August 2024 JWST data came in, and someone went back to look at that footnote. The position of the faint object JWST detected in August 2024 was separated from Alpha Centauri A by roughly twice the Earth-Sun distance. When the team checked the geometry of the 2019 VLT signal against their new detection, they found something that stopped them. The two signals, 5 years apart, were pointing at roughly the same region of the sky around the star. Not identical, an orbiting planet moves, but consistent with what you would expect if a single object had traveled along an elliptical path between 2019 and 2024. The positions did not contradict each other. Under certain orbital configurations, they fit together. This is where the baseline argument becomes important. A single detection of a faint blob near a star tells you something, but it carries an uncomfortable amount of uncertainty. It could be a real object. It could be a background source that happens to be in the field. It could be an artifact of the telescope's optics caught at an unlucky angle. When you have two detections separated by 5 years, that list of alternative explanations shrinks considerably. A background source, a distant galaxy or star sitting far behind Alpha Centauri A, does not move the same way a gravitationally bound planet would. Optical artifacts do not repeat at consistent positions across completely different telescopes and instruments years apart. A real planet on a real orbit would move in a specific, predictable arc. The consistency between 2019 and 2024 is not proof, but it is the kind of consistency that changes the weight of the evidence. The orbital period estimate of somewhere between 1.5 and 2.5 Earth years comes directly from piecing these data points together. If the object was detected in one position in 2019 and a different position in 2024, the arc it traveled in those 5 years constrains how fast it is moving around the star. Orbital speed is tied to orbital distance, and orbital distance is tied to period. 5 years of baseline, 2 data points, and the gravitational physics of a Sun-like star, that math produces a range of orbits that could connect both observations. Not one specific orbit, but a family of orbits. The team ran their million-path simulations through that family and found that a meaningful fraction of them were stable, consistent with the 2024 JWST brightness, and consistent with the planet being too close to the star's residual glare to detect in February and April 2025. The 2019 data was never strong enough on its own. That is worth saying plainly. If JWST had never looked at Alpha Centauri A, the VLT observation from 2019 would still be sitting in an archive labeled uncertain, and nobody would be writing papers about a disappearing planet around our nearest stellar neighbor. The old data did not drive the story, but it did something important once the new data existed. It gave the team a second anchor point. In science, the difference between one measurement and 2 measurements is not merely additive. 2 measurements define a line. 2 observations of the same object years apart define a trajectory. A trajectory is something you can model, something you can test against physics, something you can use to predict where the object will be in August 2026, when JWST gets another chance to look. The 2019 sighting, tentative as it was, transformed the 2024 detection from an isolated curiosity into something with a history. 2 observations years apart pointing at the same spot, with an orbital model that connects them. That is a much harder coincidence to explain away than a single data point. Alpha Centauri A does not sit alone in space. Every orbital model, every simulated path, every line of code the team ran to reconstruct the planet candidate's trajectory had to account for something that makes this system fundamentally different from our own. Alpha Centauri A has a companion, a large one. Alpha Centauri B is itself a Sun-like star, slightly smaller and cooler than A, but not by much. The 2 of them are gravitationally locked in an orbit around each other that takes roughly 80 years to complete. They are, in the most literal sense, a binary pair. And that changes everything about what a stable planet orbit around either of them looks like. The separation between A and B is not fixed. Because their mutual orbit is elliptical, the distance between the 2 stars shifts over those 80 years. At their closest approach, they are about 11 astronomical units apart, roughly the distance between the Sun and Saturn. At their farthest, that gap stretches to around 36 astronomical units, out toward the region of our solar system where Neptune travels. This means that over a single human lifetime, the gravitational landscape around Alpha Centauri A is continuously changing. A planet sitting in a stable orbit during the wide phase of the binary cycle may find that orbit tugged and distorted as B swings closer. The companion is never truly absent. Its gravity is always present, always exerting some pull on anything orbiting A. The strength of that pull varies over decades. This is not a subtle effect. Gravitational perturbations from a companion star this massive and this close can strip planets out of orbits. that would be perfectly stable around a single star. Think of it like trying to spin a ball on a string while someone periodically yanks at the string from a different angle. Some orbits can survive that interference. Orbits that keep a planet close enough to Alpha Centauri A, within a certain critical radius, stay stable over billions of years because A's gravity dominates and B's influence, while real remains a manageable perturbation. Orbits that push a planet too far from A are a different story. The farther out you go, the more B's gravity can accumulate, shift the orbit. Eventually, either eject the planet entirely or send it on an unstable path. The cutoff for long-term orbital stability around Alpha Centauri A sits at roughly 3 astronomical units from the star. Past that boundary, orbits become progressively less stable on timescales of billions of years. The candidate object, based on the August 2024 detection and the orbital modeling, appears to be orbiting between 1 and 2 astronomical units from Alpha Centauri A. That is well inside the stability boundary. The planet, if it is a planet, is sitting in the gravitationally safe zone, close enough to A that B's pull cannot easily disrupt its path. Even over the billions of years, the system has existed. This is part of why the team's confidence in the detection held up through the orbital modeling process. The candidate is not in some chaotic borderline region. The orbit that best fits the data falls squarely within the range that planetary dynamics would call survivable. That is not guaranteed. There are always variations, resonances, interactions that models can miss. But it is the kind of result that makes a detection look less like a coincidence and more like something real. A random imaging artifact would not know to place itself on a gravitationally stable trajectory. What makes binary star-planet formation genuinely hard to explain, though, is not survival, it is origin. Even if a planet can survive in the stable zone around Alpha Centauri A, getting it there in the first place is a separate problem. Planets are thought to form from a disk of gas and dust that surrounds a young star. In a binary system, the companion star's gravity disrupts that disk. It can truncate it, carve gaps in it, heat up material at certain distances, and cause it to disperse before it ever coalesces into a planet. Simulations of binary star systems at Alpha Centauri's separation and orbital geometry produce conflicting results. Some models suggest planet formation around A is possible in the inner disk. Others suggest the disk would be so disturbed during the early phase of the system's life that forming anything substantial becomes unlikely. There is no clean theoretical consensus here. That ambiguity is precisely what makes this candidate significant beyond the immediate detection. If the object is confirmed, the field will be confronted with a Saturn-mass gas giant sitting in a binary system where conventional theory has long said planet formation should be difficult. It would not disprove those models outright. There are parameter spaces within them that allow for exceptions. But it would force a much harder look at whether the models are missing something systematic about how planets form and survive around closely bound stellar pairs. Binary star systems are extraordinarily common in the galaxy. More than half of all Sun-like stars are thought to exist in multi-star systems. If planets can form and persist around Alpha Centauri A, despite its companion, the implications reach well beyond this single detection. The universe might be considerably more crowded with worlds than the single-star bias of current planet catalogues suggests. The presence of a second massive star only 11 to 36 times the Earth-Sun distance away, is precisely the kind of environment that standard planet formation models have historically said should make planet building very difficult. There is one detail in the August 2024 data that the researchers flag with particular care, and it does not make the story simpler. After everything, the disappearing detection, the orbital modeling, the binary star complications, there is still this. The object is brighter than it should be. Not dramatically, not by an order of magnitude, but measurably, consistently, in a way that falls outside what the standard models predict for a Saturn-mass gas giant sitting at that distance from Alpha Centauri A. The excess is real. The team does not dispute it, and it demands an explanation. To understand why this matters, you need to know what the models are actually predicting. A gas giant roughly the mass of Saturn, orbiting at 1 to 2 times the Earth-Sun distance from a star similar to our own, should glow at a certain temperature in mid-infrared wavelengths. MIRI measures that thermal emission directly. The brightness tells you how warm the object is, and the warmth tells you something about the mass and age and internal heat. When you run the numbers for a Saturn-like world in this kind of orbit around this kind of star, the models give you a specific expected brightness. The August 2024 detection came in above that number. Not far above, but above. 3 hypotheses are currently on the table. None of them is confirmed. All of them are live. The first is rings. Saturn, in our own solar system, carries a ring system so extensive that from certain angles it significantly increases the planet's apparent size and reflectivity. In mid-infrared, rings of sufficient mass and certain compositions can emit thermal radiation of their own, adding to the planet's apparent brightness in ways that a bare gas giant would not produce. If this candidate has a ring system, and if those rings happen to be oriented toward us in a way that maximizes their contribution to the observed signal, the numbers start to close. It is not a guarantee. Ring systems vary enormously, but the math does not rule it out, and the parallel to Saturn, already the most Saturn-like exoplanet candidate ever directly imaged, is hard to ignore. The second hypothesis is geometry. The way a planet looks in infrared depends partly on which face you are seeing. If JWST happened to observe this world from an angle near its pole rather than near its equator, the visible surface area presented to the telescope would be larger than average. More surface means more thermal emission reaching the detector. More emission means a brighter signal. The effect is not enormous, but for an object already close to the detection threshold, the viewing geometry matters. Pole-on observations of Saturn would make it look brighter too. Whether this candidate was pole-on in August 2024 is not something the team can currently determine. The third hypothesis pulls the explanation away from the planet entirely. Alpha Centauri is an old system, and old systems accumulate zodiacal dust, fine particles distributed through the orbital plane, heated by the star, glowing faintly in infrared. If there is a concentration of this dust near the location where the candidate appeared, it could be contributing mid-infrared emission that the team is inadvertently measuring alongside the planet's own signal. The planet is real, the dust is real, and the measured brightness is the sum of both. This would make the planet itself slightly cooler and slightly less massive than the raw brightness number implies, and would bring the detection back into better agreement with the models. Zodiacal dust contamination is a known complication in direct imaging at these wavelengths. The team has not been able to separate it out. What the researchers are careful to say is that none of this weakens the detection. Excess brightness is not the signature of an imaging artifact or a background galaxy. Background galaxies look different. Artifacts behave differently as you rotate the telescope. The object in the August 2024 data has the spatial profile and the spectral characteristics of something physically present in the Alpha Centauri system. The brightness anomaly does not suggest the detection is wrong. It suggests the object is interesting. Strange systems produce strange objects. A star with a binary companion at an awkward distance, an elliptical orbit that hides the planet from follow-up observations, a mass that puts it close to Saturn. All of that context makes a slightly anomalous brightness reading feel less. It's like a red flag and more like a clue waiting for a better telescope to read it. A Saturn with rings orbiting the nearest Sun-like star to Earth is not the strangest thing the universe has ever produced, but it is far from the most comfortable explanation to sit with. If subsequent observations confirm the object is real, the first consequence is simple and enormous. Humanity will have found a planet around the nearest star system, not the nearest red dwarf, not a violent flare-prone star that blasts its planets with radiation every few weeks. The nearest system containing two stars that look and behave like our own Sun. Alpha Centauri A and B have been stared at for centuries by everyone who ever thought seriously about where humans might one day go, and neither one had ever yielded a confirmed planet. Decades of searching, multiple false starts, one embarrassing retraction. If this candidate holds up, that whole long, frustrating chapter closes, and a new one opens in its place. The record it would set is worth sitting with for a moment. The closest directly imaged exoplanet to Earth currently sits at a distance measured in hundreds of light years. Most directly imaged worlds are enormous, young, and blazing hot. Gas giants still glowing from the heat of formation, orbiting far from their stars, where they are easier to isolate from the stellar glare. They are impressive detections, but they are exotic objects, nothing like the planets in our own solar system. What JWST may have found around Alpha Centauri A is different in almost every way. It is cool, it is old, its mass is comparable to Saturn's, its temperature is comparable to Saturn's, it orbits at a distance comparable to Earth's. This is not a hot, young behemoth caught glowing in the dark. This is something that resembles the kind of planet our solar system actually contains, photographed for the first time, 4.37 light-years away. No previous direct imaging campaign had reached anything close to this. The detection alone, if confirmed, redraws what the technique is capable of. Then, there is the binary star problem. Alpha Centauri A does not sit in a clean, isolated gravitational well. It shares its system with Alpha Centauri B, a companion star that swings as close as 11 astronomical units on its 80-year orbit. Standard models of planet formation in tight binary systems have long predicted that the region close to either star would be a difficult place to assemble a world. That gravitational interference from the companion would stir up the protoplanetary disk, disrupt accretion, prevent stable orbits from holding. If a Saturn-mass planet has been quietly orbiting Alpha Centauri A for billions of years despite all of that, the models are missing something important. This is the kind of discovery that does not just add a data point. It requires theorists to go back and figure out what their equations got wrong. The research team uses a specific phrase to describe what this object would become if confirmed: a touchstone object for exoplanet science. That phrase carries real meaning. A touchstone is something you return to repeatedly, something that calibrates other measurements, something against which new findings are checked. Right now, there is no planet close enough and similar enough to the giant planets in our solar system to serve that function. If this world is real, it becomes exactly that. Future telescopes would study it not once, but continuously, building a detailed portrait over years and decades. Atmospheric composition read through spectroscopy. Thermal variations tracked through seasons as it moves along its elliptical orbit. The ring hypothesis tested against more sensitive infrared data. Potential moons searched for through careful photometric monitoring. None of that level of characterization is currently possible for planets around distant stars because the signal is too faint and the angular separation too small. Around Alpha Centauri A, the geometry cooperates. The system is close enough that what would be undetectable noise around a star 200 light-years away becomes a tractable scientific question. The moon question in particular deserves attention. A Saturn-mass world on an orbit that traces through the habitable zone carries its own gravitational neighborhood with it. Saturn in our solar system has 146 known moons. Several of them are large enough to hold atmospheres. Enceladus erupts liquid water into space from a subsurface ocean. Titan has lakes of liquid methane and a thick nitrogen atmosphere. These are not dead rocks. If the Alpha Centauri candidate has anything comparable orbiting it, those objects would be sitting in the warmth of a sun-like star at habitable zone distances, 4.37 light-years from Earth. Nobody is claiming that. The data does not support that conclusion yet. But the data does not rule it out either, and the question will not leave the room quietly once serious characterization begins. There is also the matter of what confirmation would signal to the broader field. JWST was not designed for this. The team had to build a special observing sequence from scratch and push the instrument to its sensitivity limits just to get one ambiguous detection. If that detection is real, it means the capability exists. It means that systematic coronagraphic surveys of every sun-like star within 10 or 15 light-years become scientifically justified and technically feasible. The nearest star system was the first test case, and it produced a candidate. The others have not been looked at with this level of care. The question of whether planets around nearby sun-like stars are common or rare has never been answerable before. It is starting to become answerable now. All of that depends on a single telescope getting one more clear look at the right moment, and that moment is coming. The next real chance to confirm or rule out the planet candidate is already on the calendar. Based on the orbital modeling, August 2026 is when the geometry lines up again. If the planet is real and moving on one of the stable elliptical paths the team simulated, that window is when it should swing back into territory where JWST's coronagraphic mask can detect it. The team knows this. They are actively pursuing dedicated telescope time for that observation. In astronomy, getting scheduled time on JWST is not a guarantee. Proposals compete, committees review, priorities shift. But the stakes here are clear enough that the case for this observation is difficult to argue against. What makes August 2026 genuinely decisive is the accumulation of data behind it. This would not be a single isolated detection. It would be the fourth observation of this system looking for this object, after the tentative 2019 VLT signal, the clear August 2024 JWST detection, the two empty follow-up attempts in early 2025. If the planet appears again in August 2026, sitting roughly where the orbital models predict it should be, that is not luck, that is confirmation. The orbital arc connecting a 2019 hint, a 2024 detection, a 2026 reappearance, with two missed windows in between exactly where the math says it would have been undetectable, is not the kind of pattern that comes from an imaging artifact or a background contaminant. Background objects do not follow stable elliptical paths. Around Alpha Centauri A planet would. There is a second telescope entering the picture around the same time. NASA's Nancy Grace Roman Space Telescope is scheduled to launch in late 2026. It carries a coronagraph instrument designed for exactly this kind of high-contrast direct imaging of nearby stars. Roman's coronagraph was built partly as a technology demonstration, proving that the hardware can suppress starlight at the levels needed to photograph planets around Sun-like stars. Alpha Centauri A is, by any reasonable measure, the most compelling target that instrument could be pointed at. The Roman data would be complementary to what JWST's MIRI produces. Different wavelengths, different coronagraphic design, a second independent look at the same region of sky. If both telescopes detect the same object in overlapping timeframes, the conversation about whether this planet is real effectively ends. Between JWST in August 2026 and Roman sometime after its commissioning, the window for resolution is probably measured in years rather than decades. That is an extraordinary statement, given how long this system defied every previous instrument. Researchers spent the better part of 3 decades trying to find planets around Alpha Centauri A and B, watching false signals collapse under scrutiny, building more sensitive instruments, developing better subtraction methods, and coming up empty. The gap between those years of failure and the current moment is almost entirely the product of one telescope doing something no previous facility could manage. The extremely large telescope, currently under construction in the Atacama Desert in Chile, adds another dimension to the longer-term program. When it begins operations, the current target is later this decade. Its 39-meter primary mirror will give it a resolving power that makes JWST look narrow by comparison for certain ground-based applications. The ELT will be capable of imaging objects around nearby stars at sensitivities that push well below what any current observatory achieves. Alpha Centauri, sitting in the southern sky and accessible from Chile, is essentially the ideal target for a telescope built at that latitude. If the planet candidate survives confirmation, the ELT's eventual observations of this system could go far beyond simply detecting it, measuring atmospheric composition, tracking brightness variations across its orbit, probing the structure in ways that currently exist only as future ambitions. What happened over the past year has already changed how seriously the field takes this system. Before August 2024, Alpha Centauri A was a compelling target with a long history of disappointments. Now it is a system with an active candidate, a published analysis, an orbital model, a brightness anomaly worth explaining, a confirmed observation window on the near horizon, telescope proposals, Computational studies. Instrument planning documents that mention Alpha Centauri carry different weight than they did 2 years ago. The disappearing planet, whatever it turns out to be, has made this system impossible to set aside. That is the situation as it stands. The orbital models have identified the window. The team has the hardware. The math says the object should be visible. August 2026 is either the moment this becomes one of the most significant confirmations in the history of exoplanet science, or the moment the 2024 detection joins the 2012 ghost signal in a long list of things Alpha Centauri refused to give. For the next few years, every astronomer who follows this work will be waiting for August 2026 the way you wait for a verdict. Step back from the orbital models and the coronagraphic masks and the missed detections for a moment and consider what is actually happening here. Alpha Centauri has been in the sky above southern cultures for longer than written language has existed. The ancient peoples of southern Africa, the Aboriginal Australians, the navigators of Polynesia, all of them watched those 2 bright points in Centaurus and built meaning around them. Alpha Centauri A and B are so close together in the sky that to the naked eye they read as one star, the third brightest in the night sky, a fixed point that generations used to locate the Southern Cross. For most of human history, it was simply a light, something to steer by, something to name. Then astronomy arrived, and the light became a distance. 4.37 light years, 25 trillion miles, the closest star system. And once that fact was established, Alpha Centauri stopped being just a navigational marker and became something stranger, a destination, the nearest place you could theoretically go. For the last 100 years, every serious discussion about interstellar travel starts with the same 2 words. The obsession is not incidental. It is the closest sun-like system that exists. And if you want to imagine humans someday reaching another star, this is the star you imagine. All of that weight, all of that history arrives at this moment. A telescope designed to find the first galaxies, objects at the far edge of observable time, was pointed at the nearest star system. And it found something, a faint signal, 10,000 times dimmer than the star itself, sitting at roughly twice the Earth-Sun distance, glowing in mid-infrared with a warmth that matched what you would expect from a world. Not a relic of ancient light from a galaxy 13 billion years gone. Something close, something possibly right there, and then it disappeared. That disappearance is not the end of this story. The math says it is probably orbital motion. The simulations say more than half of the stable orbits consistent with the August 2024 detection would also hide the planet from JWST in February and April of 2025. The planet did not vanish. It moved. The detection window closed. That is the most likely explanation, and it is the kind of explanation that only makes sense if the object is real. But here is the thing worth sitting with. The capability itself is new. Before JWST, nobody could block the blinding glare of Alpha Centauri A precisely enough to see something that faint at that distance from the star. The coronagraphic mask, the subtractions, the specially developed observing sequence, none of that existed as a working method for this target before a team built it from scratch. JWST was not designed to do this. It was pushed into this territory because someone decided it was worth trying, and the telescope turned out to be sensitive enough to make it work. That means something independent of whether this particular candidate is confirmed. The era of not being able to see planets around Alpha Centauri A has ended. The technical barrier has fallen. Whatever is there, one planet, several planets, nothing. We now have the instruments to look with the sensitivity required to find it. Every future observation of this system will be better than the last. August 2026, if the team gets their time, will answer the question more definitively than any previous observation could have approached. And if not 2026, then the Roman Space Telescope. And if not Roman, then the extremely large telescope from the ground. The search has crossed a threshold. Decades of failed radial velocity surveys, ghost signals, and dead ends accumulated into a history of frustration. And then one instrument, one coronagraphic mask, one carefully developed observing program, produced something that the entire previous catalogue of attempts had never managed. A candidate. A real, faint, orbitally plausible candidate around the nearest sun-like star to Earth. That relationship with Alpha Centauri is genuinely different from what any previous generation had. Not just watching the light, reading it. Carefully enough that if something is there, it cannot stay hidden forever. Something is out there, 4.37 light-years away, on a clockwork orbit around the nearest star that resembles our Sun. And right now, the only question left is whether we can catch it sitting still long enough to be sure.